Let me give you some time. You might want to grab a paper if you want to write this down. Anyway, I'm gonna post this note on Blackboard as well. And then we have initial condition. We have initial velocity. So up to this point, that's the most common ODEs we've been seeing all the time during this class. So what's special about this ODE is first, is second order. When you say it's second order, just count how many dots on top of X. If you see 2 dots, that's a second order system. Sometimes you see 3 dots, that's third order system. So the second thing is single degree of freedom. So then you just count how many unknowns you have. So in this case, your unknown is only X. You have 1 unknown. So that's why we call it a single degree of freedom. It's also a linear system. That means your M, C, K are constant. Right? And then it's also a stable system. That's when we say M, C, K, they're all positive. So when you see such an equation, we can say that's the second order single degree linear and stable. So linear systems give us the property of superposition. All right, so remember the linear system, that's pre-assumption is very important because a lot of conclusions we drew in this class is based on superposition. All right, so what's next? So that's one way to see your equation. The other way to see your equation is sometimes we want to convert it to standard format. The way you did these is you just normalize everything by the mass. And then you have your undamped natural frequency, omega n, that's k over m square root. Your zeta is just c over 2mk. All right. So that's everything we need to know about the equation itself. Then let's look at your FT. What FTs we can use? The first condition is when FT is 0. Very, very simple. That's something we learned in part number 1. We call these free vibration. Oh, one thing I forgot to mention is, so in this class, we mainly target zeta greater than 1, greater than 0, smaller than 1, or the underdamped condition. I'm not saying that all the method we learn only applies to this condition. It's just we use this special case to simplify our discussion. All right. So for free vibration, FT, no force, then we already know that the response is something like AE minus zeta omega n t sine omega dt plus phi. And then omega d, we call it damped natural frequency. So it's a function of omega n, and it's a function of your damping ratio. And then how to find your A and phi. So then you need to go back to lecture number 3, slide 7. So your A and phi are determined by initial condition. Okay, and then the geometry, or I mean the time domain function of these xt would look like something like this. Initially, it moves in a really large amplitude, and the amplitude decays exponentially. That's everything we need to know about free vibration. when force equal to 0. So we learned these in part 1. So in part number 2, we deal with this very special type of force, which is harmonic. When we say it's harmonic, then we have two forces. It's either a sine wave or a cosine wave. So that means you only have a single frequency component in your force excitation. So how to solve these equation then? So you have to go to your math 333. And then, or you can go back to lecture 8, slide 4. Over there, we discuss how we solve these systems. So this system actually xt equals to xht plus hpt, right? So the first one is a homogeneous solution, or sometimes we call it transient state. The reason it's called transient is because these systems, eventually these xh part dies out over time. So the xp, which is called particular solution, if you're taking an ODE class, but in vibrations, we call it steady state. So only the second part survives as time goes by. So we already learned some special tricks to find the steady state. So these tricks to find steady state, that's called Bode plot or transfer function. So you just do Laplace transform, I should say Laplace transform. You do Laplace transform, find the Bode plot, and then find the transfer function. And then you don't have to solve the equation from the scratch. You just need to, then you can directly find the amplitude, find the phase lag of your response. So how the response look like, your hxt part is, always remember your homogeneous part is associated with initial condition. So that means your xht is going to give you a prime e minus zeta omega n t psi omega dt plus 5 prime. And then your particular solution is going to be the steady state amplitude times sine omega t plus theta, which is the phase lag. So remember, the big X amplitude and theta are from Bode plots. And then how to find your A prime and theta prime? Then you need to plug your initial conditions back in. And what do you do then if you don't remember how to find these A prime and phi prime? Just go to slide number 4 in lecture 8. Okay. So that's for part 1 and part 2. Starting from part 3, we learned a ton of different excitations. The first one is called impulse, when ft is a half hat delta t, or we call it impulse. Right? So how these ft look like? T, that's for ft. Ideally, it's something like this. The magnitude of these is f hat. And that function only exists when time equal to 0. So that's called an impulse function. So what's the response for this impulse? Details can be found in lecture 11, slide number 3. So the key point here is impulse is equivalent to initial velocity. But then remember, during the class, because this impulse is a sharp change at that time point. So that initial velocity is different from x naught and v naught. So your x naught is x 0 prime 0 minus, v naught is x dot 0 minus. So that means the initial conditions you apply to the system, that's actually before time, that happens before time equal to 0. And then this new initial velocity, which is f hat over m, that's actually happened after time equal to 0. So that might be a little bit confusing. But if you don't remember or understand these, what you need to do is you just need to remember what these xt look like. Eventually becomes f hat over ht. So what is ht? It's just a response of the unit impulse. So ht, the response of unit impulse. So I can write these ht for you. Is 1 over m omega d e minus zeta omega nt sine omega dt. So if during the exam, if you do need to use ht, you don't have to express it out. You can leave the ht there. I can understand. All right. So that's when your impulse is at time equal to 0. Your final response is just xt, the amplitude of the impulse times the unit response. That's actually superposition because your system is linear. So whatever response, so that means your response linearly increases with respect to the magnitude of the excitation. If ht is unit excitation, then if you apply an f hat increment in your excitation, then your response is just multiplied by the same ratio. All right, so sometimes you're going to see time lag or time delay. For example, in that case, you have time, you have your ft. Your impulse is no longer happen at time equal to 0. If it happens at some point like tau, okay, so that means your ft is f hat times delta t minus tau. So if you see t minus tau in your function, that means that equation is delayed by tau seconds. So the same thing, because it's a linear system, if you delay your excitation by tau, then your response will be delayed by tau as well. So your xt would be f hat ht tau, right? You just delay your response by tau. One thing you also need to remember is this is only true when time is greater or equal to tau. If it's smaller than tau, you have no response because the excitation hasn't arrived yet. Make sense? All right, so the other way to write these is you can use a so-called phi function, t minus tau. So these phi function is called Heaviside function. What it does is it's a piecewise function. It equals to 1 when x is greater than 0. It equals to 0 when x is smaller than 0. Okay, so these functions is nothing special. It just helps you to better write the piecewise equation. So this is your xt when your initial velocity, when x naught and v naught are 0. Or your system is initially at rest. But then during the class, we have an example. I forget which one, but I can easily give you one here. X1, let me see. let's say this is f theta t, x naught not equal to 0, v naught not equal to 0. So if you have an equation like this, you want to solve it. So in this case, let's see what kind of excitations we have. We have impulse excitation, right? But you also have initial condition. So your initial condition is also a type of excitation. That's the first type, that's the free vibration. So that's why you also have to consider that as one type of excitation. So that means you have 1, 2 excitations. So that means you have to divide your system into 2 subsystems. The first one is due to X naught and V naught because it's free vibration. You have to go to lecture 3 and then find out your X. The solution for the subsystem 1 is A e minus zeta omega n t sine omega dt plus phi. And then your second subsystem is the impulse. So your second solution would be f hat ht. And then finally, your solution would be whatever solutions you got from each subsystems. So the reason why I would like to start this review is I'm using this black color to highlight the basic excitations you've seen during the class. So initial condition, that's one type of excitation. One harmonic is one excitation. One impulse is one excitation. If in a problem like this one, if you see both initial condition and impulse, that's actually 2 excitations. You have to use superposition to divide your system into 2 parts. Make sense? So, any questions? Right. So if no questions, I'm going to move on. So we already reviewed 3 different types of forced excitation. The 4th excitation, that's something we learned during the class, is actually arbitrary force. That means your FT can be anything. It's the most general format. So what we get is your xt is going to be integration from 0 to time f tau ht minus tau d tau, or 0 to time ft minus tau h tau d tau. So this equation is called convolution integral. It applies to any force input. The backbone for this equation is that your Ft is equivalent to infinite number of impulse excitations. You can treat the forced excitation as if they are infinite number of impulse excitations, and then you just use superposition to lump all these excitations together. You're going to get an Ft. So during the class, we never actually talk about the arbitrary force excitation. We just focus on one special case, which is Ft equals to a step function. So how does it look like? So your ft, your time, your ft, is a step function with the amplitude of f0. And then this jump happens at time equal to 0. So if you want, you can go to lecture 11, slide 8, to find the solution for this. So the solution is xt f0 over k minus f0 k1 minus zeta squared e minus zeta omega n t cosine omega dt minus theta. And then your theta is invert tangent zeta 1 minus zeta square root. So if you don't remember the response, I can draw it for you. So your xt will be something like this. And then in that plot, you have the peak time, you have the rising time, you have the offset, you have the overshoot. You're going to see your response doesn't directly reach that bias point or reach the offset. You're going to see overshoot, oscillation, and eventually it stabilizes around the bias point. So that's the response when you have a stepped input. So we also mentioned about what if your stepped response has been delayed. What if you have a step function with time delay? So then your function would be something like this. And then let's say this is tau, this is f0. Again, if your input is delayed by a certain period of time, you don't have to do anything for you. You don't have to do a lot of things to your time domain response. You just delay everything by tau. So the way you delay this is you just replace all time by time minus tau. Then let's see what we have. So all the constants, they stay the same. And then minus zeta omega n. You see t here, that becomes t minus tau. And you see cosine omega d, another t over there becomes t minus tau. The same theta states. That's the response when you have a certain period of time delay. And remember, once you have time delay, then your response becomes a piecewise function. So this is only true when t is greater or equal to tau. And then if it's smaller than tau, then you have 0. Again, you can use the Heaviside function to merge the piecewise expression. All right, so that's another building block when you have a step function. How many we have right now? Okay, we have 5, we have 6, which is when ft is periodic. So any function that is periodic falls in this category number 6. So the way we do these is you want to go back to lecture 12, slide 4. The first thing we need to do is do Fourier transform or Fourier series for any periodic signal, periodic and continuous signal. You can convert your ft into a summation of harmonics. So for each periodic force can be decomposed into a lot of harmonics, all right? So that means if you use superposition, you just have infinite number of harmonic excitation. So what you need to do is you need to go back to building block number 2, because over there we provide the solution for a single harmonic excitation. Here, the only difference is you have infinite number of higher harmonics. So then you just calculate that one by one. And usually you don't have to go all the way to infinite, because as I said during the class, at high frequency, your response is getting weaker and weaker. So sometimes you're going to stop at 5, you can stop at 10, 20. It's going to be a finite number. So that means, let's say, I think in lecture 12, homework 2, I said your n should be 10. So let's assume this is 10. If it becomes 10, then how many harmonics you have? You have your static response, you have n cosines, you have n sines, and then remember you always have your initial condition, x0 and v0. So that means you're going to have 2n plus 2 subsystems. So for each subsystem, using one of the building blocks, to solve them, and then just lump them together. All right, I think interesting. The good news is I record the entire session. So if you do have the questions, I'm going to post the videos right after these. I think Zoom is not doing great today. All right. So that's when you have like a periodic signal. So I highly recommend you to go over homework number 2 in lecture 12. I'm gonna highlight this. I'm 100% sure you're gonna see these in your exam 3. Make sure you understand that part, because as I said, it's 2n plus 2 subsystems. Make sure you know how to do it in MATLAB. Otherwise, it's going to be crazy if you want to do this by hand. All right, so I'm going to go over these example next Monday. But before that, just check it out. All right, so the last one is, the last case is Laplace transform. That means when your ft can be transferred to S domain. So for some special ft functions, you can find that Laplace transform. So then you can use the Laplace and iLaplace in MATLAB, or you can search the Laplace transform table to find the response. So the table is actually in lecture 13. All right. Actually, the last case, I might missed it. The last case is superposition. you're going to see for example, I think in lecture 11, you already see that whenever you have an impulse like this, you can decompose it into two step functions. That's your T1, that's your T2, T1, T2. So sometimes when you have a really complicated FT, you can decompose it into small basic elements and then lump the solution together. I can name a few here. So for example, if you have a stage function like that, that's a T1, that's a F naught. It can be decomposed into two slope functions. That's a T1, that's a F naught plus, that's your T1, that's 2T1, that's minus F naught. So for the slope function, you can use Laplace transform to solve it. Or sometimes you're going to have a two-step function. That's T1. You can decompose it into step function number 1 and step function number 2. Right? So you can sometimes for these complicated excitations, you can just decompose them into simple formats. All right. So any questions? I'm going to post these documents online, so no worries if you cannot write all of them down. And I'm going to post my video right after this.